Alright, okay, let's go. Okay, so introduction. The first sentence of this introduction was supposed to be interpreters are magical. One of the earliest reviewers who wishes to remain anonymous said that sounds super stupid. Christian, I don't think so. Still think that interpreter are magical. Let me tell you why. On the surface, they look deceptively simple. Text goes in and something comes out. They are programs that take other programs as their input, produce something simple, right? But the more you think about it, the more fascinating it becomes. Seemingly random character letters, numbers, and special characters are fed into the interpreter and suddenly become meaningful. That is true. The interpreter gives them meaning. It makes sense out of nonsense. The computer, a machine that's built on understanding ones and zero, now understands and acts upon this weird language we feed into, thanks to an interpreter that translates this language while reading it. I kept asking myself, how does this work? And the first time this question began forming in my mind, I already knew that I'll only be satisfied with an answer if I get to it by writing my own interpreter. So I set out to do so. Audiobook, article, blog post, the tutorial on interpreter exists. Most of the time, though, they fall into one of two categories. Either they are huge, incredibly heavy on theory, and more targeted towards people who already have a vast understanding of the topic. Message. Okay. One of the main sources of frustration was this latter category of resources because the interpreter, they explain only interpret languages with a really simple syntax. I didn't want to take a shortcut. I truly want to understand how interpreter works, and that included understanding how Lexical and parser works, especially with a C-like language and its curly braces and the semicolon, where I didn't even know how to start parsing them. The academic textbook had answer I was looking for, of course, but rather inaccessible to me, behind their lengthy theoretical explanation and mathematical notation. One of the main source of frustration was this latter category of resources. Okay. What I wanted was something between 9-page book on compiler and blog post that explained how to write Lisp interpreter in 50 lines of Ruby code. So I wrote this book for you and me. This is the book I wish I had. This is a book for people who love to look under the hood, for people that love to learn by understanding how something really works. And in this book, we going to write out our own interpreter for our own programming language from scratch. We won't be using any third-party tools or libraries. The result won't be production ready, but it won't have the performance of a fully fledged interpreter. Of course, the language it's built to interpret will be missing features, but we are going to learn a lot. Okay, it's difficult to make generic statements about interpreters since the variety is so high and none are alike. But what can be said is that the one fundamental attribute they all share is that they take source code and evaluate it without producing some visible intermediate result that can later be executed. That's in contrast to compiler, which takes source code and produce output in another language that the underlying system can understand. Some interpreter are really small, tiny, and do not even bother with a parsing step. That's interesting. They just interpret the input right away. Look at one of the many brainfuck interpreter out there to see what I mean. On the other end of the spectrum, a much more elaborate type of interpreter, highly optimized and using advanced parsing and evaluation technique. Some of them don't just evaluate the input, but compile it into an internal representation called bytecode, then evaluate this. Even more advanced are JIT interpreter that compile the input just in time into native machine code that gets executed. But then in between those two categories, there are interpreters that parse the source code, build an abstract syntax tree out of it, and then evaluate this tree. This type of interpreter is sometimes called tree walking interpreter because it walks the AST and interprets it. What we will be building in this book is such a tree walking interpreter. We are going to build our own lexer and our own parser, our own tree representation, and our own evaluator. We'll see what tokens are, what an abstract syntax tree is, how to build such tree, how to evaluate it, and how to extend our language with new data structure and built-in function. Every interpreter is built to interpret a specific programming language. That's how you implement a programming language. Without a compiler or interpreter, a programming language is nothing more than an idea or a specification. We're going to parse and evaluate our own language called Monkey. It's a language specifically designed for this book. Its only implementation is the one we're going to build in this book, our interpreter. Okay, expresses blah blah blah, seeing blah blah blah. Okay, that's fine. Okay. Easy file without noticing the title and the word girl in it. First of all, congratulations as per your macro, blah blah blah. I like writing code in Go. I enjoy using the language and standard library and tools it provides, but other than that, I think that Go is in possession of a few attributes that make it a great fit for this particular book. Go is really easy and subsequently easy to read and subsequently understand. You won't need to decipher the Go code I present to you in this book. Even if you are not an experienced Go programmer, I'll bet you can follow this book along even if you've never written a single line of Go in your life. Another reason is that great tooling Go provides. The focus of this book is the interpreter we are writing, the idea and concept behind it, and its implementation. With Go universal formatting, thanks to Go formatting and testing framework built in, we can concentrate on our interpreter and not worry about the testing framework built in, blah, blah, blah. I think much more important is that the Go code presented in this book maps closely to others and possibly more low-level languages like C, C++, and Rust. And maybe reasoning for this is Go itself, with its focus on simplicity, its stripped down charm and lack of programming language construct that are absent for other languages and hard to translate. Or maybe it's because the way I chose to write Go for this book. Either way, there won't be any meta programming tricks to take shortcut that nobody understands anymore after 2 weeks, and no grandiose object-oriented design and pattern that need pen, paper, and sentence. Actually, it's pretty easy to explain. Okay, let's just start. Okay. Chapter 1, Lexical analysis. In order for us to work with source code, we need to turn it into a more accessible form. As easy as plain text is to work with in our editor, it becomes cumbersome preview files when trying to interpret it in a programming language as another programming language. So what we need to do is represent our source code in other forms that are easier to work with. We are going to change the representation of our source code 2 times before we evaluate it. Source code tokens to abstract syntax tree. The first transformation from source code to tokens called lexical analysis, or lexing for short, is done by a lexer. It's also called tokenizer or scanner. Some use one word or the other to denote subtle differences in behavior, which we can ignore in this book. Tokens themselves are very small, easily categorizable data structure that are then fed to the parser, which does the second transformation and turns the token into an abstract syntax tree. Here's an example. This input 1 gives to a lexer, and what's come out of the lexer looks kind of like this. Makes sense? All of these tokens have the original source code representation attached. Let, in this case, plus sign, some, and so on. Some, like identifier and integer in our example, also have the concrete values. They represent attached 5, not 5 in the case of integer, and x in the case of identifier, but what exactly constitutes a token varies between different Lexical implementation. As an example, some Lexical only convert the 5 to an integer in the parsing stage, or even later, and not when constructing tokens. A thing to note about this example, white space characters don't show up as a token. In our case, that's okay, because white space length is not significant in the monkey language. White space merely acts as a separator for other tokens. It doesn't matter if we type it like this or we type it like this. Okay, that's fine. So let's break this down. First of all, there are number like 5 and 10 that are pretty obvious. Then we have the variable names x and y, and add the result. And then there are also these part of languages that are not numbers, just words, but no variable names either, like let and fn. Of course, there are also a lot of special characters. The number are just integers. We're going to treat them as such and give them separate type. In the Lexical parser, we don't care if the number is 5 or 10. We just want to know if it's a number. The same goes for the variable names. We will call them identifier and treat them the same. Now the other words, the ones that look like identifier but aren't really identifiers since they are a part of the language, are called keywords. Okay, like for example let and stuff like that. We won't group these together since it should make a difference in the parsing stage whether we encounter a let or fn. The same goes for the last category we identify, the special character. We'll treat them each of them separately since it is a big difference whether or not we have a parenthesis or parenthesis in the source code. Let's define the token data structure. Which field does it need? As we saw, need type, integer, blah blah blah. Okay, finally get the code. Alright, token go package token type. Oh man, Copilot disable. Type token struct type token literal string. Okay. We define token type to be a string. So between using string also has the advantage of being easy to debug without a lot of boilerplate, and help a function. We can just print a string. Of course, using a string might not lead to the same performance as using an int or byte, but for this book, a string is perfect. And as we just saw, there's a limited number of different token types in monkey language. That means we can define the possible token type as constant in the same file. We add this. Okay, constant legal. Actually, Copilot might be helpful for this. How do you accept this? Oh, Control J. Okay. Delimiter. Phrase. Okay. Keywords. Function. Let. Okay. We didn't see them in exam above, but we'll need them. Illegal signifies a token character we don't know about. And EOF stands for NFI, which tells our parser later on that it could stop. So far so good. We're ready to write our Lexer. Okay. Before we start to write the code, let's be clear about the goal of this section. We're going to write our own Lexer. It will take source code as input and output the tokens, output of the tokens that represent the source code. It will go through its input and output the next token it recognized. It doesn't need to buffer or save tokens, since there will only be one method called next token, which will output the next token. That means we'll initialize the Lexer without source code and then repeatedly call next token and on it to go through the source code token by token, character by character. We'll also make life simpler by using string as the type for our source code. Okay. Disable. I think disable. That's fine. For testing monkey token. Func test next token T. Okay. Input plus test struct an array of type expected type token, not token type, and expected literal string and token dot assign plus friend. Wait, is LSP? No package. Commodinate. Okay. Okay, how the heck did this work? I see. Okay. Alright. That makes sense. Alright, let's go back to this. Alright, new input. Wait, Copilot. Is it on again? Okay, don't have new yet, that's fine. Rain test. Toke. L next token. Okay, I need to go, actually. If toke time I go on TT not expected. Fatal. Don't test Lexer. Don't test. Cool. Okay. I think this should be a good stop. Pick point.